Hello, my name is Trikudinov, and in this video I will be presenting the work me and my colleagues have prepared for IROS 2022, the IEEE/RSJ International Conference on Intelligent Robots and Systems. Our work focuses on the problem of concurrent design, or co-design for short. Co-design is an approach that automates the robot design process and motion planning together. We parameterize the robot design by a vector rho and find the optimal design. To do so, we minimize the user-defined costs, such as energy. The co-design cost is also on the robot motion, which is computed for a given task. This motion is a set of states and controls that are discretized in time. The robot motion or trajectory is computed by a motion planner, which is formulated as a nonlinear optimal control problem. In this paper, we formulate a bi-level optimization, where this trajectory is computed in the lower level by the motion planner, and the optimal design is computed in the upper level. We additionally specify constraints and bounds on the design variables in the upper level. To solve the bi-level optimization, we adopt a gradient-based approach. We take the derivative of the motion planner in the lower level. Here we use the chain rule to show the different components of this derivative. This derivative is complex and requires differentiating through the motion planning. To do so, we can use finite differences directly on the cost, without having to separate it using the chain rule. We can leverage the fact that the dimensions of the design is relatively small, up to 17 dimensions in this work, and use parallel computation to speed up this process. Here we show the full approach. We use the derivative computed by parallel finite differences, as we described, and embed the motion planning into a nonlinear program that we solve using the commercial solver Knitro. This allows us to specify arbitrary equality and inequality constraints on the design in the upper level. Our full pipeline also involves verifying our approach in a second phase, where we fit a proportional derivative controller in simulation. This allows us to validate the improvements in co-design cost. We need to fit the best controller, as the robot's mass and dimensions require different gains to execute the motion successfully in simulation. We consider two tasks, trotting and jumping. We first define an upper level cost on the electrical and frictional energy of the robot, and then optimize for both tasks. We also specify a set of constraints. We specify a nonlinear constraint on the positions of the payloads, which are the inertial measurement unit or IMU and motherboard or MB boxes. We also specify a set of linear constraints on the design variables, including the width, height, and depth of the base and the attachment points of the legs of the base. Finally, we optimize for both the robot morphology and its actuator parameters, namely mass and gear ratio, as illustrated on the right. Here we show the optimization process for trotting. We plot the energy cost and display the robot design at every iteration. The robot motion is displayed at every 5 iterations, though it is considered at every iteration by the optimizer. This optimization took 2 minutes and 36 seconds for 35 iterations. Our co-design approach finds different optimal designs for the two tasks, where for trotting, the center of mass is lower and the robot is heavier, and for jumping, the robot is lighter as the entire mass needs to be moved. The heavier motors are more energy efficient with significantly less electrical losses. However, for jumping, lighter motors are better, as the electrical and friction losses are less than the effort needed to jump with a heavy robot. We see that these designs indeed lead to significant improvements in cost. These improvements also carry over in simulation. Finally, we compare our approach to a sampling-based algorithm, namely the covariance matrix adaptation evolutionary strategy, or CMA, which is a popular algorithm that is used for solving co-design problems in the literature. We vary the dimensions of the design vector and run the optimization for both tasks. For CMA, we varied open parameters and plotted the mean and one standard deviation for both costs and time to 99% convergence. We see that we can achieve similar co-design costs as CMA across problem dimensions. However, we see an improvement in scalability and timing compared to CMA. This is important for interactive co-design tools, as well as for extending the approach to multiple tasks or scenarios in parallel. This is the end of our presentation, and if you have any questions, please feel free to contact me by email. Finally, I would like to thank my co-authors, Carlos, Vlad, Steve, and Setu. Thank you.